Today we're going to look at the stability of closed-loop systems. We have done analysis on transient, on steady-state error. All those analyses were under the condition, on the assumption that the system is stable. That is, the system reaches a final steady state and settles at a given point. It does not diverge to infinity, it does not become unstable. So today you're going to address a criterion and a method to determine whether or not the system is stable and for which range of certain parameters the system is stable and unstable. So by the end of the lecture, you should be able to understand what stability means, define the conditions required for stability, and apply a method called the Routh-Hurwitz stability criterion to determine whether the system is stable or not, and in some specific cases, for which range of certain parameters the system is stable. There are several applications of this. When we deal with a system, there is for example, in the human body, there is always some sort of stabilizing feedback. The system itself is stable. And in several different situations, the system, the body is regulating a process to maintain stability. Here's one example, is very simple, is equilibrium. We have a center of mass, and you try to maintain that a center of mass at a certain angle. And once that a center of mass goes beyond the a certain axis, we cannot stabilize the body anymore, and we may fall. But until then, there is a certain range where the body is trying to actively maintain balance by controlling your position and orientation. But past a certain point, we may reach a point where stability can no longer be maintained, and then the body itself becomes an unstable system. Without control, we can say that the body is unstable, but there is an active action of the body that occurs at all times to maintain that stability. There are many systems that are either inherently unstable and we can stabilize using a control, using a feedback control, but there are also systems that are stable without control that we can make unstable if we don't design a controller properly. We need to be very careful in that regard. We can make systems stable, but also unstable. Are these systems here, for example, stable without feedback control? Well, none of them are. Now, when you ride a bike, you are actively maintaining balance. You're actively taking some sort of action to maintain balance. And if no action is taken, then a bike is unstable, it will fall. And the same for the other two. There is a controller that measures the orientation and then applies a torque to the wheels to make sure that you are always in a vertical position. So there is an active control loop, there's an active logic behind it that is designed to maintain a certain position, to maintain stability. And without data control system, all of these systems here are unstable. But you can also make a stable system unstable if you don't design a controller properly. Here is one example of that. What you are doing when you develop a controller is to measure something, compare with a reference, and then create an error and then apply an amplified version of the error as a control input. But let's consider this example here, for example. We have a microphone, just an individual using a microphone with speakers. So we take the voice, amplify the voice, send that to the speakers. If they are too close, what happens? The speakers will now pick up on the voice that is amplified in the speakers, send that back to the feedback loop, and then the feedback loop will keep amplifying the voice, which in theory should tend to infinity because you're amplifying a positive feedback loop now. The more we amplify the voice, the more sound the microphone can pick up, and that signal is then sent back to the speakers that is amplified again and again. So this is an example of a positive feedback that destabilizes a otherwise stable system. But if the gain is small, then maybe the microphone cannot pick up the voice from the speakers and the system is stable. Maintaining stability. Beyond a certain amplification, the system becomes unstable. Here is another example, simple to understand. So let's where a high control gain can make a system unstable. Let's assume, for example, you're having a shower and we want to regulate the temperature to a comfortable level. So what we do is that we control the valve by opening and closing the valve to control the temperature. So in our head, we have a desired temperature. We take a look at how the water feels, right? That's our sensor, and we create an error. If the water is too cold, well, we move the valve to the hot position. If it's too hot, we go the other way. That's a negative feedback loop. I said the controller here is the human itself. The output of our control action is the valve position. So the valve position now regulates how much hot or cold water we are injecting in the system to change the temperature. So that goes through the hydraulic system, and the hydraulic system has its own response time. It has inertia, it has a transfer function, it doesn't change temperature immediately. It takes some time. So now let's assume that the human controller that we develop here is simply a proportional gain K. So what happens if this gain is too high? Well, if this gain is too high, then we assess that the temperature is not hot enough. We'll create an error. We multiply that error by a very large gain, and that determines the valve position. So we would move the valve all the way to the hot setting. The temperature starts to rise. It will take some time. And as it starts to rise, there is some inertia. The desired temperature goes beyond the temperature we wanted. Now it's too hot. The error flip sign. Now the temperature is too cold. It's too cold. Sorry, it's too cold. Sorry, it's too hot. So the error becomes now negative. We want to decrease the temperature. We multiply that by a constant K. And the result of this operation is that our controller determines that the valve now needs to go all the way to the cold. And then you repeat the operation, go to the cold. Now the water starts to cool down. It has some inertia. It will go beyond the temperature we want. It will become too cold. And what we do? Well, the error will flip sign again. And then here we go again, all the way to the hot water. And you're stuck in the shower forever. And that's an example of an unstable system. If your proportional gain is too high, if you're not patient, will make the system unstable. And the result of this operation is that you just put the valve all the way to hot, all the way to cold, and you oscillate around a desired temperature without actually settling at that temperature. We can take any mechanical system and do the same with a controller. If our gain here is too aggressive, a system that is otherwise stable can get unstable with improper control. So we can define the concept of stability generally in three different cases. The first one is a stable system. We have this cone here, and if you apply a small displacement to this cone, it will move and then eventually come back to its original position. It reaches an original position again, and it settles there when you give a certain input. So the system is said to be stable. When subjected to an input, to a bounded input, it displays a bounded behavior. The second case is a neutral system, where the system is not stable nor unstable. It's a system in the center. What happens if you apply an input to it? Let's say a small impulse. Well, it will just keep spinning. It will keep spinning forever if there is no friction. So this system is said to be neutral because it does not stabilize, does not destabilize, it just keeps moving indefinitely. The last case is the unstable system, where the system is in equilibrium, maybe in equilibrium like that, but as soon as we apply any input to it, it will fall. It will never reach that condition again. So for a bounded input, it will display an unbounded output. That's the concept of stability. When we apply this concept of stability to a transfer function, we have a very simple statement that is a sufficient and a required condition for stability. And that is that a system is stable if all of its closed loop transfer function poles lie in the left half of the S-plane. In other words, all poles of the closed loop transfer function of the entire system with feedback has poles with negative real parts. Remember that the real parts of the poles will generate exponentials, and provided that the real parts of the poles are negative, then the system will eventually settle somewhere. These exponentials decay to zero. So that's a sufficient and the required condition for stability. We can see this more clearly from a transfer function. If you take this generic transfer function, which is simply multiplication of poles and zeros, the output for this transfer function is as in equation 2, is a very generic transfer function. You would see something like in equation 2. The first element there comes from the real poles, and the second sum comes from the complex poles. We see that both of these elements have an exponential. And provided that the poles have negative real parts, they lie on the left side of the S-plane, then everything decays to zero and the system reaches stability. If there is one pole, at least, that does not meet that condition, that is on the right side of the S-plane, that has a positive real part, then one of these exponentials will tend to infinity, and the whole transfer function, the whole expression for the output y of t, will also tend to infinity and will make the system unstable. Okay, so a necessary and sufficient condition for a feedback system to be stable is that all poles of the system transfer function have negative real parts, so all these exponentials decay to zero. If at least one pole has a positive real part, that is sufficient to make the entire system unstable. Okay, now apply. Yep.
In the last slide, what was n again?
N was just poles at the origin here.
Okay, got it. Thanks.
Yeah, so we can disregard that. Now, if you apply this concept to the S-plane again, so long as we have poles located here, the system is stable. If the poles are located along the imaginary axis, this will characterize a neutral system or a marginally stable system. That's the second case we saw, because when we apply an input to it, there is no exponentials, there is only sinusoidal components, and they never decay. So the system is said to be marginally stable. The poles are purely imaginary numbers. And in the last case, an unstable system, then you cross into the left side, right side of the S-plane. If the poles are located there, then the system is unstable. Right? So that's the unstable zone. And when we are when you have a stable system, then you remember we may have an overdamped, underdamped, and so on. So if you want to assess the stability of a closed loop system, all we have to do is to determine where the poles are. Here's an example of a marginally stable system. We have this transfer function, 1 over s plus 10, s squared plus 16. What are the poles of this transfer function? Well, we have 3 poles. We have s equals to negative 10, and you have s equals to plus minus 4j. So this pole here is real. This pole here is imaginary. So the real pole is located on the left side of the S-plane. It's negative 10. So this will create an exponential that eventually decays to 0. The other 2 poles, however, they are located on the imaginary axis, and they will generate sinusoidal waveforms that never decay. And when you plot the time response for this should be a step input, this is what happens. We have initially a transient that in this case here is very small, so we can't see. And eventually we are left with, after the exponential decays, we are left with the sinusoidal waveform, and the system continues to oscillate indefinitely. Right? So even if we have only one pair of poles located on the imaginary axis and everything else is stable, it is sufficient to keep the system oscillating indefinitely. In the same way that it is sufficient to have a single unstable pole to have an entire system to become unstable.
I have a quick question.
Mm-hmm.
Since like the s squared plus 16 is like just imaginary, wouldn't that be neutral?
It will be neutral, yes. This is not unstable. This would be a marginally stable system. Yeah.
Okay, yeah. Okay.
Okay.
So, but why does it still oscillate indefinitely? Oh, okay.
It oscillates indefinitely. If we had an unstable system, then we would have an exponential that increases.
Oh, to infinity. Okay. Okay.
Professor, just a quick question here. So for this one seems that it starts from 0. It is begin like the sinusoidal wave, but in this case, it should not be like the start from like the exponential wave and the real part became 0 and then became the sinusoidal wave only.
Yes, correct. Yes, as I said, the transient here is small, we can see, but it should be something like this.
Okay.
Where you have initial exponential here that will disappear.
Okay, because this one is just to start from 0, so I thank you.
Yeah.
Professor? So in the previous slide, you had said that in neutral system, the poles are purely imaginary. When this one of the poles isn't imaginary.
Yep. Yes.
So, but does do the imaginary poles just counteract that one?
The imaginary pole or the unstable pole will dominate the response. So if you have a system with 50 poles and one of them is unstable, the entire system is unstable. If you have a pole with a system with 50 poles and one of them is purely imaginary, that is sufficient to make the entire system marginally stable.
So should the condition on this slide be at least one pole is purely imaginary?
For marginally stable?
Yeah.
Yes. Yeah.
Okay.
Yeah.
You.
Well, we always have two, right? Imaginary poles always come in pairs.
I have one question here. So like just like what you mentioned, if there is only one pair of imaginary pole, like there are several like the real pole, in that case, the stable time will take longer.
Not necessarily. Not necessarily. It doesn't depend on how many poles you have. It depends on how the magnitude of the pole itself. So if you have, for example, 1 over s plus 10 plus a, this would be in time domain exponential of minus at. So the larger a, the farther it is from the imaginary axis, the faster it disappears.
Okay. Okay, good to know. Right. Thank you.
Any other questions? No? Okay. So our job now is to assess the stability of a system. Is very simple. We just need to determine whether or not we have poles on the left or the right side of the S-plane, or if they are sitting on the imaginary axis. If you want the system to be stable, the poles need to be on the left side. So here is one method to assess that, is the Routh-Hurwitz stability criterion. This is sufficient condition and required condition for stability, and is simply a way for us to determine where these poles are. You may say, well, I could just use MATLAB for this and just find the roots of this equation. Well, that's true, but sometimes we want to evaluate a range of stability where one of the parameters in the transfer function is not fixed. So this will come in handy in those cases. This is the idea. I'm not going to explain how the Routh-Hurwitz stability criterion was derived. That's for the mathematicians to do. We're going to accept it as it is, and we're going to apply it to our problem. So the way this condition was derived, there are calculus textbooks out there that would explain this very well for us. All we need is to apply this to our problem. We'll take the transfer function and define what we call the characteristic equation. And the characteristic equation of the transfer function is simply the denominator, where the poles are. It's the denominator of the transfer function. And we will arrange the coefficients of this equation in a matrix, as in equation 5. And we'll do some sort of operations. So all these coefficients will come in the first two lines of the matrix, and then we'll fill out the other lines using some basic operations that we're going to see in the next slide. And once that is completed, we have to look at the first column here and count the number of times the sign of those coefficients change. For each sign change in the first column, that indicates a pole that is on the unstable region. So a sufficient condition for stability and require is that this column here never changes sign. It must be all negative or all positive. So the number of roots with positive real parts equal to the number of changes in sign in the first column. Now, of course, you need to figure out how to fill out this matrix, but you'll see it's relatively simple. And this is the Routh-Hurwitz stability criteria. So the first thing we're going to do, once we define our characteristic equation, which again corresponds to the denominator of a transfer function, is to place the highest order of that denominator in the top left column, ranging from n to 0, where n is the degree of that transfer function. So if we had a transfer function in this, for example, s times to the power of 3 plus 2s squared plus s plus 1, we would start with s to the power of 3 and go down all the way to the power of 0. So that's our first step. Easy. Now, once this is completed, we now need to fill out the first two lines in this matrix. And these two lines will take the coefficients of the transfer function. So the first one here, the highest coefficient goes there. The second one multiplies s minus 1 goes there. The other one goes here. The other one goes there, and so on. So you see this up and down pattern. Highest coefficient, and then just decrease the coefficient of s. And you go up and down. In the example that I gave here, we would go with the coefficient that multiplies s to the power of 3 first. That's 1. Then you go immediately under it is the coefficient that multiplies s to the power of 2, that is 2. And then now we go back up. Let me add the number 3 here just to avoid confusion. If plus 3s, we would have 3 and 1. So again, we go down and up and down and up. So if you got this properly, in the first row, we should have the coefficients of all odd powers of s, in this case, and in the second row we have the even one. So of course this only applies to because we have s to the power of 3. If it was s to the power of 4, you would swap the odd and even numbers. Okay, so that's step number 2. All good so far? Any questions so far? Yeah. All right, now let's move on to step number 3. Now I have to fill out the other rows that are under it. So we know how to do the left one, we know how to do the 2 above there, and now we need to fill out the next ones. So let's start with the first number, which is b n minus 1. So if you take b n minus 1 here, here is the expression for it. Let's see what it gives. It takes the determinant, or what is just above it, so this one and that one, see an times an minus 3 minus an minus 2 times an minus 1, and we divide that, the entire thing, by the negative of the bottom left element. By the negative of the bottom left element. We'll do an example. This will become more clear. So this would be b minus 1. If we now go to b minus 3, we can repeat the operation, but now we stretch the determinant by one column. So instead of taking the first 2, we take the first one here and the third one. And then you do the determinant like that. And we again divide this by, an minus 1, which is always the top, the bottom left in the operation. And if you stretch that one more, if you go to b minus 5, then this one would move to the next, and so on. We'll do an example soon. Those will make more sense with numbers.
Professor, I have a quick question here. For the A part, if like sum of the part is 0, like there is s to the power of 3, and there's no s to the power of 2, and there's only a s and plus 1. So what it should be?
Should be 0.
Yeah. Okay. Got it.
Right.
Thank you.
So if it was something like this, we put number 3 here. We would have S4, S3, S2, S1, S0. And then on top we have 3, 0, 1, 2, 5, and 0 again to complete. Where this 0 here corresponds to the coefficient of s to the power of 3, which is not there. And this 0 here is just required to complete the top row. There's nothing after 5 that goes to 0.
Oh, okay. So here it is doesn't matter how many here it is. We need to finish the 2 line, right? Like
Yes.
here, okay.
Yeah, always finish that with 0. So, okay, so now we calculated the second line here, the third line. Now let's move 1 down. When we move 1 down, we repeat the process, and you just move everything down by 1 line. So if you're now dealing with this element here, Cn minus 1, we'll take the determinant of what is just above it, divided by the negative of this element. And that's what equation 12 gives. If you now want to do Cn minus 3, this element here, then you're going to expand the determinant, take these 2 and these 2, find the determinant between them. We'll see equation 13. And then we divide that again by the negative of the same value. And so on until we complete the array. Let's do an example. That'll make things a lot easier to understand. So here we have a characteristic equation. There's a 5th order transfer function. And you have s to the power of 5 all the way to s to the power of 0. The first thing is to create the left column here. Because we have a power of 5, we go from 5 to 0. Power of 5 to power of 0. The second step consists of filling up the first 2 lines. And you can see that you're now taking the coefficients of the transfer function there. And you notice again how we go up and down, moving to the right. If any of these coefficients is not there, it turns out to be 0. So we had here, if the coefficient s to the power of 3 was not there, then this number 1 here would become 0. Okay. Are we good here?
Yep.
Yeah. All right. So now let's do the first element in the calculation, which is this one. When you calculate that element, then you have to take the determinant, what is just above it, and consider the corner here, the bottom left, to calculate the new coefficient. So what is this new coefficient here? Is going to be the determinant of that, which is 1 times 4 minus 1 times 2 divided by the negative of this. And this is equal to -1, right? 4 minus 2 is 2 divided by -2 is -1. So this element here is -1. Now let's move on. Let's do the next one. That's this one here. So for that one, we'll take this column that column, and again consider the bottom left there. What is the determinant? Is 1 times 10 minus 11 times 2 divided by -2, which is
6.
6. So this element here is 6. Now we need to calculate this element. So we have to stretch the matrix, and there's nothing there, so this is 0 and 0. So here we have 1 times 0 minus 0 times 2 divided by -2, that's 0. Now let's go one
Sorry,
down.
Professor, could
Yep.
you please repeat the matrix for the last one you just did? The 0 on the third line.
So 1 times 0 minus 0 times 2 divided by -2, which is 0. All right, so long as every time we run out of numbers there, it will become 0. So now let's do this element down here. For that one, now we move everything down by one line when you're dealing with this and that. So what is the value here? How do you calculate
60.
that? 2 times 6 minus 4 times -1 divided by -1, which is indeed 16. So the number down here, 16. Are we good?
Yeah.
Yeah. Now what is this one here? This one will take this column, that one. And this number is
10.
2 times 0 minus 10 times -1 divided by -1, which is 10. The next one is
0.
0. Now when expand, we'll get 0 again. What is this one here? Is my -1 times 0 times 10, sorry, times 10 minus 6 times 16 divided by
-60.
-16, which is 6.625. So this is 6.625. What is the next element? Is -1 times 0 minus 0 times 16.
0.
It's 0. All right, so it would be -1 times 0 minus 0 times 16 divided by -16, which is 0. So this is 0. And the next one is also 0. And what is the very last one there? I'm running out of colors here. What is that one? Is 16 times 0 minus 10 times 6.625 divided by negative 6.625, which is
10.
10. And then everything else is 0. We completed the array. Now what do we do next? Well, now we have to evaluate the sign, the number of times the sign changes in the first column, and it changes twice. Why twice? Because from 1 to 2 there is no sign change. From 2 to -1 there is one sign change. From -1 to 16 there is another sign change. From 16 to 6 there is no sign change, and from 6 to 10 there is no sign change. So there is 2 sign changes. What does it mean? It means that this system has 2 unstable poles. It has 2 poles located on the left side, on the right side of the S-plane.
Sir, Professor, could you go over the sign changes again?
Yeah, so if you go down, starting at 1, from 1 to 2 is both positive, no sign change. From 2 to -1, the sign has changed from positive to negative, so that's 1. From -1 to 16, we're going back to positive, so the sign has changed again. 16 to 6 and 6 to 10, they're all positive, no sign changes. So the -1 goes positive, negative, negative, positive, 2 sign changes, 2 unstable poles. Any other questions? No? Let's do another one then.
So in case if the system is stable, then there's no sign change in the first column, right?
Yeah.
Okay.
Which can be achieved by having either all positive or all negative numbers.
Okay, thank you. There is a case if there is a 0, how can we
We'll deal with that
consider
later. Yeah.
Okay, thank you.
Professor, I have a quick question about the criterion. Not this criterion, but like if you had for a transfer function that there was one pole on the imaginary axis and one pole like on, well, 2 poles on the imaginary axis and one on the right side, would you consider the system unstable or marginally stable?
What do you think would happen? Would they have there? Let's think about it. Would they have an exponential that goes to infinity, and you have poles that oscillate indefinitely? So the one that goes to infinity brings everybody to infinity. The system
so
is
that one
unstable.
has, so in terms of like effects of the poles, so
Unstable?
the positive real poles have like a greater effect, and then the next greater effect is the system oscillating indefinitely, and then there's the poles on the left hand side.
Correct, but we don't need the recipe to memorize that. Like, let's assume, for example, that we had poles on all regions. The pole on the left side would do something like that, exponential of -at. The pole on the imaginary axis would do, say, sine of omega t. The pole on the right side would do exponential of plus bt. If a and b are positive numbers, this goes to 0, this oscillates, and this goes to infinity. So everything goes to infinity.
Okay, thank you.
Right? Let's do this one now. We have another matrix here, another characteristic equation. Notice that the coefficient of s here is missing. We have s to the power of 2 and no s. So s to the power of 1 is 0. The coefficient is 0, and it has made it there. So let's do the first element here. What is this one?
-1.
-1. Very good. How do you calculate it? 3 times 1 minus 2 times 1 divided by -1, -1. Already we can tell the system is unstable. I already have one sign change. The whole thing is unstable. But let's continue. What is the next one?
-3.
Next one is -3. How do you calculate it? 3 times 1. Oops, that looks like a plus sign. 3 times 1 minus 0 times 1 divided by -1, which is indeed -3. Next one is 0. What is the one under -1?
-2.
Let's see. Now you're dealing with this determinant. Oops, this determinant here, and that's 1 times -3 minus 1 times -1 divided by -1. Don't get confused here with don't mix up the signs here. Right? So this is indeed -2. Very good. What is the next one?
1.
1. The next one will be 1. So we have now to expand like that. So 1 times 0 minus 1 times -1 divided by -1, which is indeed 1. Next one, 0. What is the one under -2?
-3.5.
Very good. -3.5. You guys found it? -3.5. Now we do this determinant here. -1 times 1 minus -3 times -2. Don't get mixed up with the signs there. Minus 2, which is indeed -3.5. Next one is 0. Next one is also 0. And the one under -3.5 is
1.
1, which is -2 times 0 minus -3.5 times 1, or 1 times -3.5 divided by -3.5. You can notice something interesting here. Anytime we have a 0 that shows in the second row, shows on the second part of the determinant, the number that you are calculating will be exactly what is just above it as a shortcut, right? Just a little shortcut. So that's it. Now we have the entire row completed. How many unstable poles do we have?
2.
2. 2 unstable poles. From here to there is no sign change. From here to here, there is one sign change, no sign change, no sign change, and another sign change. So there are 2 sign changes, 2 unstable poles. Indeed. Any questions? No, this is very simple. You'll see it's always the same. Just takes some practice. No questions? If there are no questions, let's move on. Now let's analyze some special cases. So there are 3 special cases we need to take into account. We know how to deal with it. We can fill out the matrix, count the number of changes of signs in the first row. The easiest case is where the entire column, not row, sorry, the entire column here has non-zero elements. That's easy. We know the sign of a non-zero element. For this particular system, if A0, A1, and A2 are not 0, then a sufficient condition is that all of these are positive or all of these are negative for the system to be stable, no sign changes. That's the easiest case. The second case is when there is a 0 in the first column and all other elements in the row containing the 0 are non-zero. There is a 0 in the first column and all other elements in the row that contains the 0 are non-zero. So for example, if you take this polynomial and you do the matrix for that polynomial, this particular element here will be 0. 1 times 4 minus 2 times 2 divided by -2 is 0. And this would create a problem because when you calculate C1, we would be dividing that by -0. And then it blows to infinity. And you also notice that what is just next to 0 there is a number 6. So the elements there are not all 0. There is something that is not 0 there. So that's what characterizes case number 2. What can we do? Well, if we encounter a 0 and all other elements in the column are not 0, in the row, excuse me, are not 0, then just write a variable, in this case here I'm using epsilon, and do the remaining calculations using epsilon. For example, the one that I have here just under epsilon, which is I call it C1, is 2 times 6 minus 4 times epsilon divided by -epsilon. It's now a function of it, and now I've just flipped the sign. That's what we see here in C1. Multiplied both the top and the bottom by -1. And you will now see that a D1 will be a function of C1, which is a function of epsilon. You can calculate the entire column using now a function of epsilon. And once that is done, then we make epsilon tend to 0. And you make epsilon tend to 0. In this case, I'm choosing to make it tend to 0 from the positive side because the number just above it was positive. And what happens then? Well, when epsilon tends to 0, what is the value of C1? It tends to -infinity. 4 times 0 is 0. -12 divided by a very, very small positive number tends to a very large number. And the system tends to -infinity. So C1 tends to infinity, -infinity, which is a negative number. The system is already unstable. We can do the same for D1. If 6C1 with C1 tending to -infinity minus 10 times 0 when epsilon tends to 0 is 0, divided by something to -infinity, this will actually tend to a finite positive number. So D1 is positive. So here we have negative. We have a positive. Epsilon is a positive small number. So this is positive, negative, positive. And how many sign changes we have? 2 again. And the system is unstable. Okay. Let's do case number 3. And case number 3 is very similar, but now all other elements in that row containing the 0 is 0. So here we would have a 0 and everything else is 0. In this polynomial here, I had s plus 2s3 plus 2s squared plus 4s plus k. Filling out the polynomial like that, we can see that now the row of S1 has an element that is 8 minus k divided by 2. When k equals to 8, the entire row is 0. And when that happens, that means that we have purely imaginary poles. And the system is marginally stable. Anything greater than 8 will make that a negative, and you have 2 unstable poles. So k equals to 8 would be the limit of stability in this system. Up to 8, everything is positive. At 8, a row of zeros imaginary poles. K greater than 8, make that a number negative, 2 unstable poles, and so on. Okay.
Professor, in the case 2, in which situation we consider the epsilon approach to the -0?
If everything else was negative, which is very rare, you would make it approach 0 from the negative side. But if you have positive coefficients, then make it positive.
So you mean which part? You mean the first column are all negative?
If you have everything negative, then you can make it approach negative from 0 from the negative side.
What do you mean here for everything negative? You mean all of the numbers?
All numbers in the first row are negative.
Okay, got it. Thank you.
Can I ask a question?
Yeah.
If, for example, let's say we have 3 numbers in the third row, and the first and the second one are 0, but the third one should be 0. Let's say we in a row with that starts with 0, we have, like, for example, 2 other zeros and 1 non-zero number. Is that also like case 3?
No, that would be case 2. Case 3 requires all elements to be 0. Yeah. If you go back here, you can see that there is another element of 0 in the row of epsilon, and but it is also number 6 there. That characterizes case number 2.
Oh, got it. Thank you.
Okay. All right, let's do an exercise a bit more complicated. These ones are kind of boring. Let's skip them. We can do them later. There's the solution there. There's just the raw calculation that we did, very similar to what we did before. Let's do something a bit more exciting. Let's do this one. Yeah, let's do that one. So here we have a laparoscopic arm that operates under feedback control on the patient, and this is the controller that was developed for it. We know that what omega going down is. That's the disturbance that we're going to neglect. And this controller has 2 gains, Kp and Ki, and they are used to regulate the arm's position. We'll see how to derive that later and what Kp and Ki do. So you're doing position control, neglecting the disturbance, and with this controller, we want to know the limits of stability as a function of Kp and Ki. So find the characteristic equation of the closed loop system, and then use the Routh-Hurwitz stability criterion to find the range of Kp and Ki for which the system is stable. That's not it. That's not it either. There it is. What is the characteristic equation of this system? Well, the characteristic equation is nothing other than the denominator of the closed loop transfer function. And what is the closed loop transfer function for this? Assuming that there is no disturbance, as the problem specifies. What is the characteristic equation? That is y over r. Let's find the transfer function now. The transfer function is this times that, Kp s plus Ki all over s multiplied by that plus s plus 20 divided by
1 plus that part.
plus 1 plus that. Yeah, 1 plus the same thing. How do you solve this next? Well, find a common denominator here, which is this. Multiply it by 1. then simplify the denominator with that. I think at this point, we can skip that derivation. We have done it so many times. I'll just give you the final answer here. 10 times kps plus ki. And then if you have any questions, let me know. S squared plus s times 10 kp plus 20 plus 10 ki. Now notice here that I'm grouping everything that has the coefficient of s. Right? We have two terms. When you multiply this out, you have to put them together because they constitute together the coefficient of s. What is the characteristic equation? Well, it's the polynomial here in the denominator. That's our characteristic equation. We have a third order system starting with the power of 3, and we now want to know for which range of kp and ki the system is stable. So now let's take this polynomial and use the Routh-Hurwitz stability criterion, starting with s to the power of 3, s2, s1, and s0. And let's complete the array here. What are the coefficients here? The first one is, right there, is coefficient of S3, which is 1. The second one is this coefficient of S2, which is also 1. The coefficient of S is this entire thing, 10 kp plus 20. And the coefficient of S to the power of 0 is 10 times ki. Are we good? Yeah? What is this coefficient here? Let's call this A. What is A? A is 1 times 10 ki, 1 times 10 ki, minus that times 1, divided by
-1.
-1.
Minus 1.
Okay, that's coefficient A, and A is then what we have, 10 kp plus 20 minus 10 ki. Let's see. What is this coefficient, this number here? Well, we are stretching it to the top to 0, 0. So this is 0. And what is this one? Because you have a 0 here, there's going to be 10 times ki, but let's calculate it. It's going to be, let's call this B. B is 1 times 0 minus 10 ki times A divided by negative A, which is 10 ki. So this is 10 ki. We good?
Yes.
What is the condition for stability now? No sign changes in the first column, which means that A must be greater than 0, B must be greater than 0. If these two conditions are respected, then the system is said to be closed loop stable. Right? So if you have positive, positive, everything is positive, no sign changes. When B is greater than 0, we can go here and say now that a 10 times ki must be greater than 0. So the first condition is that a ki must be greater than 0. we can apply the same condition to this one and say that A must be greater than 0. In that case, we write 10 kp plus 20 minus 10 ki to be greater than 0. Move 10 ki to that side. We can divide everything by 10, and you can get ki that is smaller than sorry, let's do kp. Ki, we have a condition for ki there. Let's do kp. We have 10 kp, or just kp, greater than ki minus 2. I just divide everything by 10 and move these two terms to the left, to the right of the equation. So these are the two conditions. Ki must be greater than 0, kp must be greater than ki minus 2. And if this is this condition is respected, then the system is closed loop stable.
Professor,
Yep.
wouldn't it be ki over 2 minus 1? Because there's 20 kp.
Where is 20 kp?
Oh, is it only 10 kp?
Yeah, it's 10 kp. Sorry,
Oh,
yeah, this
okay.
it looks like a 2, it is 10. Yeah. Oh, 10.
Professor, so if the
Yep.
question is asking for the unstable states, we just assume one of them smaller than 0.
If ki is smaller than 0, what would happen? Then kb.
No, I mean, we just assume like A smaller than 0 or B smaller than 0, then we just can have the condition of the K and KP.
Yeah, yeah. So if if A is now smaller than 0, it would be 2 unstable poles. If B is the one smaller than 0 only, then you only have 1 unstable pole.
Yeah, and both of them is negative, then there's one stable.
If
So
if both are negative, then there would be only 1 unstable pole.
Okay.
Okay, let's do exercise 4. So wheelchair velocity control system is shown in the diagram. Determine the maximum gain K1, K2, K3 for a stable system. You guys found the closed loop transfer function. Y over S, Y over R. What is it? It's everything here multiplied, divided by 1 plus the same thing. And this should be K divided by, I'm going to give the final results here, so that will save some time, because this is, at this point in the game, should be trivial. Plus K, where K is K1 times K2 times K3. Okay, this will save us some time. Do the same process, this multiply divided by 1 plus that multiplication, then multiply everything out, factor out same coefficients for S is 3, 2, 1, and 0. And this is what we get. So we'll skip this so we can focus on the rest. So you have our characteristic equation here. Now let's do the Routh-Hurwitz array, s to the power of 3 all the way to s to the power of 0. Now I can look at the coefficients there, 0.125, 0.875, 1.75, and 1 plus k. Let's call this element B. And let's call this element here. This is one we calculate later. What is the value of B? B is 0.125 times 1 plus k minus 1.75 times 0.8. So minus 1.75 times 0.875 divided by negative 0.875. So you can recalculate this, and this gives the value of B as 1.607 minus 0.1428 K. What is this number here? This one is 0. What is this one?
1 plus k.
1 plus K. Now we can see
1
that if you do 0.875 times 0 minus 1 plus K times B divided by negative B is 1 plus K. What is the condition for stability?
B bigger than 0 and 1 plus k bigger than 0.
Correct. B must be greater than 0, and so does 1 plus K. So from this condition, we can see that K must be greater than negative 1. That's for the second condition. The first one, you need B to be greater than 0. So I can write 1.607 minus 0.14 28K. Want this to be greater than 0. So K must be, to satisfy that, K must be smaller than 11.25. K is smaller than, just so for this, 11.25. So what is the range of K for stability? K needs to be greater than negative 1, but is smaller than 11.25. If this is the range of K, then the system is closed loop stable.